Hello, everyone, and thank you for joining us today. My name is Sean Sullivan, and I will be your host for this Technology Gateway webinar on NASA Langley's Electric Field Imaging System. Our featured presenter today is Dr. Ed Generazio. Dr. Generazio is based at NASA Langley Research Center in Hampton, Virginia, where he works as a research physicist as well as the agency's non-destructive evaluation, or NDE specialist. As NDE specialist, Dr. Generazio provides guidance to NDE personnel agency-wide and serves as NASA's NDE representative to other government agencies. In his 30-plus year career with NASA, Dr. Generazio has over 100 publications and has received numerous awards, including NASA's Outstanding Leadership and Distinguished Service Medals. Following Dr. Generazio's presentation, we'll also hear a short talk from Jennifer Viudez, a licensing specialist at Langley Research Center. She will be speaking on how NASA Langley partners with outside organizations through technology licensing. Now, before we get started, I'd like to point a few things out. Your microphones are going to be muted throughout this entire presentation, so if you have any questions, please type them into the chat box and we'll answer them during the Q&A session towards the end of the webinar. At this point, I'm going to turn it over to you, Ed.
Thank you. Electric field imaging technology is a remote imaging of electrostatic potentials and electrostatic fields in and around objects and in free space. Electric field imaging, with electric field imaging, you can characterize electric charge distribution, and this creates a new field of study that embraces areas of interest, including electrostatic discharge mitigation, crime scene forensics, the design and materials selection for advanced sensors, the dielectric morphology of structures, the inspection of containers, inspection for hidden objects, tether or wire integrity, and development of organic molecular memory. Also some applications in medical diagnostics and treatment. So I'm going to cover some of these areas. I want to start off first showing you some of the basics of what you need for electric field imaging, how it's working. This is an array circuit. There's a component here. This is a field effect transistor called a FET, and the FET has a gate, a source, and a drain. In this particular diagram, there's a whole array of them because I'm going to use arrays later on. I'm going to show some of the results from that. But the difference here from other FET circuits and other the ways you use FET circuits is that the gate does not have any electronic components connected to it, and that's contrary to all specifications because you always want to protect the gate from any electric field, strong electric fields, because generally the FET will break down if it gets a strong electric field and it arcs, and you'll lose your FET operation altogether. But that same sensitivity is exactly the sensitivity that you want when you want to build an electric potential sensor. So we're going to base our system on this design here. This is a high impedance on this end, and there's a low impedance on the outside here that you get your measurement from. That's one of the basic elements that you need for electric field imaging. Now if you take that particular array and you make a linear array going along here, vertical array, if you put a source for electric field over here, and this is called a quasi-static generator. I'm going to use a source. You don't have to use a source all the time, but I'm going to show you a source because it's been very helpful in the development of the sensors. But this is a quasi-static generator, which I'll show in a little bit. It's a dipole field, and it rotates around, and there's an equipotential plate here. And with this configuration, you have an equipotential here, and you have in an infinite plate approximation, you have a uniform electric field going across the volume here. And if you have an object present, then if there's an object present, the object present will distort the electric field as it comes towards the sensors here. So it's very similar to an airport inspection system where you have like an X-ray machine and a detector, and you're putting your baggage through this conveyor, and there's a conveyor showing here. So you can actually scan your object. In this case, it's not X-rays, it's an electric field that you're using to interrogate the object. There's some coordinate system down here, X and Y, Z shown here. There's a sensor array. And this is typical data that you would get. I'm not going to show all the data, but there are a lot of waveforms. This particular quasi-static generator is moving around slowly and is slowly changing the potential on this plate, indicated here by B surface. And you're monitoring that voltage at the sensors due to the rotation of the slow rotation of this quasi-static generator. From this information, you can actually generate an image, electric field image, electric potential image, and electric potential image of the object, of the electric potential along this plate here, along this array. Since you have a conveyor, you can create a two-dimensional image from that information. This is one of the first ones. I made two images in the beginning, and this is probably the second image. And I'll say that this is a self-portrait, and it's a person standing on that conveyor belt. And this is an electric potential image of that person, and you can see the knee, calf, waist, and chest areas, and part of the shoulders. There's the dimensions here. This is in inches. And over here, away from the person, this is the electric potential away from the person, without the person there. And you can see that there's changes here in these areas, pretty dramatic. Over here, some image processing. Again, I want to point out this is one of the second images that I ever did with this system. With the image processing, I didn't have image processing in place at the time, but I just used a canned package from image processing software packages. And this is one of the first results that I got with that image processing package. There's no physics in this package, by the way. I'm just pointing out that it's just intensity related. And I had cotton pants on and cotton shirt, but I also had polymer socks on. You can see these bright areas here. And I'm not making a claim that I've got this is what I have, but this is very interesting to see this occur in this place, these lines here, and also the sock area showing up there. You'll see that's very important later on, why that's like that. I then moved on to composite compression specimens, and these are optical images of the front and the back of a compression test specimen. And you can see in the front there's a crack going across it here, and in the back there's also a crack on this side, and these are the dimensions. This is the electric potential scanned in that system that I just talked about. Far away from the object is the uniform potential without the object present. You've seen that here. It goes to the mean value here, a uniform value. As you approach the object, the potential actually increases, dark, and then it decreases near the support brackets. It's these support brackets up here. So you're actually seeing a really complex distortion of the field shown here in these 3D views. You can see it's actually buckled out and then buckled in around the object. And so these are electric potential images of this object in a uniform electric field. Now you can go further. Now that you have the electric potential in that plane, you can also get the electric potential at a different plane, two different planes. So you can go near the specimen or away from the specimen. You collect these two images. These are electric potential images. With this information, you can collect the X component of the electric field. You can collect the Y component of the electric field, and you can also collect the Z component of the electric field. With these three images here, of these three components, and some basic math, you can estimate the electric field in the plane of the array, and this is what that electric field looks like. So this is an electric field magnitude, and what we're seeing here is there are high magnitude fields around the edges of the bracket that I showed earlier, both the top and lower bracket, and you can also see some indications of cracks on the front and the back sides. So this is the first electric field image magnitude done, and this is the inverse of that image above there. So basically you're seeing the sources of the high strength sources of that field. You can go a little further now, and when you have objects and you touch them, whenever you touch an object, you leave or pick up electronic charges, depending on what the materials are, how they're dissimilar, triboelectrically dissimilar. But whenever you touch something, or two materials touch each other and can come apart, they become charged for a period of time. And so we took this ABS gun. This is a polymer gun, gun simulator, and the reason we were doing this is for security. Some ABS gun simulators may not have any metal content, so they're not detected by conventional systems, inspection systems. This is an all polymer gun placed into a packing container. This is the polymer container here also, and then it's closed up. And if we image this container using that same system that I just showed you, you get this kind of result here. This is the equipotential image of that container overlaid onto the container here. So it's a composite photograph, composite image. And you can see the electric potential of the gun is the base of the gun. This is the barrel of the gun here. But you can also see what we believe to be the fingers that actually touched the foam after it went into the container and was sealed up. And I want to point out that this image was taken. This image was here. It was done 24 hours after the packing, and it's believed that these charges last many days. So this just happens to be 24 hours later. So this becomes an inspection capability that you can do with electric field imaging. We can go a little further now, and if you take, I had a person walk across a rug. This was a anti-static, it's actually anti-static protection rug for offices. And I had a person walk across. This is the optical image of the rug. And these are the 3 footfalls that they took across the rug. Then I imaged the rug with electric field imaging, and you can see where the person's foot touched the rug, where the heel touched the rug, and where the toe left the rug. On and up, you see 3 footprints. But you can also see, if you look carefully, you can also see the treads of the shoe that actually walked onto that rug. So you can see not only the direction that's going in, but you can also see the object, start to see the structure of the object that was present on the rug. This was done 5 minutes after the rug was walked on, and that was primarily because of the arrangement was needed to actually make that image. But and an image was also made 24 minutes later, very similar to this one, but it's believed that these charges that are left by folks walking across rugs and things like that last for many days. So you actually have another forensics tool that you can use for electric field imaging. I wanted to show, this is a video of the first electric field imaging system, and this is a wire here going through the actual sensing array, this 2D array, and the potential of the wire is being changed, and you see the potential, these are LEDs, they're changing illumination according to the strength of the electric field coming out of the wire. This is an insulated wire. I'm just changing the potential on that wire. You can see it's radio. But most importantly is down at the bottom here. I'm going to let it go again. Is that when you try and measure the potential of an object, this is passing right through the sensor, which made it a little bit easier. But if you look down at the bottom here, the structure that's actually holding this sensing system is actually affecting the measurement. So that's another key element that you have to watch out for when developing the electric field imaging system. This is a video of the quasi-static generator, just so everybody can get oriented to see what it is. This is a dipole system. There's a positive and negative element. It's basically a double Van de Graaff generator, and it's been put into a triboelectrically neutral container. It has a low dielectric susceptibility. And in this case, I used wood. You don't have to use wood. There are other materials that you could use. Wood was easy to work through, and I just wanted to show you what it's like. And it can go at a variety of speeds, depending on what kind of data you want to take. The next question is, now that we can see inside of a container, we can see objects, non-moving objects inside of a container. Can we see the electric potential of an electronic circuit inside of a container and look at the potential variations inside that container? Look at where the potential variations are occurring inside the container on the electric circuit, and we do that remotely. So this is we're going to show the video of imaging a strobe circuit, which is a camera strobe. This is the camera strobe here. This is a 2D array. This is one of the first ones built. I put a piece of wood in front of it to assure that I wouldn't shock my sensors, because I didn't know what kind of potentials the system would work with. And here you're seeing, it's basically in slow motion, but you're seeing 6 flashes per second. And this is not an optical image. This is an image of the electric potential of what's going on inside the circuit in the strobe light. So you're looking at variations of the elements charging and discharging inside the strobe light, and you're seeing that remotely. Another area of interest is plasmas. Plasmas are charged particles, and there's a wide variety of sources of plasmas. I'm going to show some of them, but I first want to start off with an ion gun and look at, in this case, it was an ion gun developed for electrostatic discharge mitigation. And this is, I'm going to image the output of the ion gun. This is the array, this is another array, and this is the ion gun head over here. And then this is the 2D image, real-time image. It's actually slow motion in the sense it's about 1,000 frames a second, so it's faster than typical real-time. And you're seeing this is the negative here, strong low potential is the gun itself activated. You can see the flow out here going around out in this area here. I want to point out there's very little image processing here, so there's been very little contrast enhancement, So there's a lot of work in terms of software that needs to be done. This is just a crude measurement, a crude display of actual results to show that we had results and it's working properly. These dots up here are sensors that are failed. Same thing over here. And you can kind of get a uniformity of the system by the calibration of the system in this particular figure right here. And so there's some optimization in that area. Combustion is also has charged particles. So I wanted to look at that. So I started out with an electronic, just a conventional lighter. These are some of the systems where you have electron densities, plasma electron densities. I'm going to look at flames. And here again, you see those failing sensors up here. This is the lighter trying to ignite. It didn't ignite. Here's the lighter again trying to ignite again. And here's the ignition, and you're seeing the flame, the area of the flame. And I did not make a video of the flame at the time, but since this is the first time I tried it, flame going around. And I did not have a thermocouple in place at the time, so I didn't know the relationship of the temperature of the sensor, the E-sensor, with temperature. But I now know that if this variation in temperature was due to heat, that this would be darker than this out here, not lighter, the opposite. So we're seeing charged particles in the flame as it moves around the system. Again, the same failing sensors up here. And these, you can see the modeling in the background here is different manufacturers that made the particular FETs, and I've identified that as an area that you have to watch. And there's more in this flame that's of interest that's coming, that when you turn the source off, there's a extinction ring that shows up. And I'm going to try and show that shortly. The rings are about this zone right here. You'll see them in this zone here. You can see the extinction. I asked thermal folks to do thermal camera work, and they said most of the thermal camera work with flames is they're trying to look through a flame to see the other side, not to image the flame. But we're seeing extinction rings. So there's more science coming forward in this particular area. Okay, those are some of the demonstrations that I put together to give you a flavor for what you can do with electric field imaging. There's a whole lot more, and I haven't shown some of the stuff that we do have. But I'm also, every time I turn one of the systems on, I come up with a new result that has to be explained so you can make a next step into a particular area. So it's actually expanding out, like fingers, or expanding out with more and more activity and interest areas. But so let me go through some of the commercialization opportunities as I see them. The ones right up front is the real-time manufacturing of cable integrity for extended lengths, in terms of tethering the insulation integrity, and also for high voltage cable insulation integrity. You can actually monitor the cable as it's being made and look at the fields coming out of the cable in real time. Also, for national power grids and city power stations, looking at the power distribution integrity, where you may have leaking transformers, leaking wires, etc., and we have subterranean transport systems and things like that, where you're looking for citizen safety and working. You have citizens around voltages. Other areas, I showed you the container and the baggage inspection area, where you're looking at hidden components. I've started some work showed you some of the work in electronic signature, electronic components. I didn't show what the actual component was because I hadn't taken that particular strobe light apart, but I've done other work to show that you can actually identify the elements that are being charged and discharged within a circuit, and you can do this remotely outside of the container. You can also determine if that circuit is activated or not, and that's a security issue of interest. Also, leakage electric fields. If you're building a system and you want to check to see if it's leaking fields around it, you can identify where the leakage source is, because now you have a measurement of the electric field vector, and you know exactly where the field's coming from. You can also, if you're trying to suppress electric fields from your system, or you want to transmit them in a particular the characterization direction spectrum, you can look at those transmission suppression quality systems to see if they're working properly and enhancing electric field imaging. Also, one of the things I've noticed with electric field imaging is that as I build new systems, the electric field imaging system is actually defining what new material I should use to build the next system. So they're coming out better and better as I come up with new systems. So electric field sensor material selection is coming forward as an area. I talked about ESD mitigation. You can also set up standards for dielectric properties of materials, and as well as, and this hasn't been done well before, is identifying the triboelectric properties of materials. Now you have a method to identify the standards, to develop physical standards for triboelectric properties of materials, and that affects all sorts of areas, manufacturing, all measurement science, and also triboelectric materials compatibility when you have things moving around, even with microsensors and things like that. At the micro level, if they're moving around, you're going to get triboelectric charging. And so knowing the triboelectric properties and compatibility of these materials is important for developing those sensors and systems. Other commercialization opportunities are the characterization of thin films and contamination. I haven't done any imaging of that, but we're looking at charges that not at an atomic level, we're at the even smaller level because there's basically singular charges on the surface. So it's a little bit, it's smaller than the atomic level, so we're looking at that. So you can actually have charges on top of contamination for those that are interested in that area, and you'll see those charges on the contamination. So that area, again, I want to point out I haven't done that area, but that area is likely to be very fruitful. Because we've seen the ABS gun 24 hours after it was placed into the container, this is an indication that we can store information on these polymer systems, and we already know we can leave charges in, for instance, Teflon for 50, 100 years, so we actually have all the basic needs, all the basic parts that we have to develop an organic memory that has molecular storage density, so that area can be worked and be very fruitful. The other thing is an electric field sensor. I use very durable electric field effect transistors during the development of these systems, and I still am, but there are FETs that are 100 times more sensitive that could be used. You have to be more careful about how you're going to contain them so that they don't get discharged or they don't see arcing. You're going to have to protect them, and that can be done. That's just a matter of identifying which materials are the best ones for containerizing your electric field imaging system. But you can enhance your sensitivity orders of magnitude from what I'm currently working on. And right now, perimeter security is one I can already see with an ephemeral sensor, which is a rotating sensor, and it goes on. It exceeds my room right at the moment, so it doesn't even like me in the room with it. Forensic commercialization opportunities is forensics recovery of time history events. There is no system out there for looking at where people walked in rooms, and that would work on polymers also. So vinyls and things like that, not necessarily have to be rugs. It can be other things. Micro and nano systems is another area where if you're developing, for example, micro mirrors on the order of 20 micron square systems, we have very small micron mirrors and you're controlling them with electrostatics, for example, and you want to understand what the electrostatic field is doing in controlling those systems. There's no reason why you can't use electric field sensing systems because the electric field, the FET itself, the element may be in the order of microns anyway, so you're actually making it more into the dimensions that it likes to be. We usually have it come out to a more macroscopic thing that we can carry around in our hands, but there's no reason why it can't work and will work at the micron level. So you can have a very small inspection system. And also medical applications. I haven't done cardiac imaging yet, but I believe that cardiac imaging is right on the forefront as well as part of the nervous system, and that's imaging the electronic functions or electronic circuitry of the heart, and as well as the neurons, and that needs to be done. But again, that would be done. There is another element. You have to add the software for common mode rejection, which would have to be, that definition has to be modified for this particular process because you have an array of sensing systems, and you have to address a common mode rejection for that and get through that type of filtering. The other thing I want to point out with that statement is all the images that you saw, there's very little filtering that was done. There's very little graphics that was done. I use GW Basic. I write all my data by pixel onto the screen, so that's what you saw. There's no image processing in between the data, the real data, and the pixel, other than the grayscale changing in pixel by pixel writing of that. So the whole area could be done. All that software area has to be maybe expanded greatly. Don't need to use a quasi-static generator for illuminating systems, as I showed with the that I showed earlier. You can use solid-state electric field imaging system, and there you've actually embedded the quasi-static generator in a solid-state level, in with the FET. So the FET itself becomes the generator as well as the receiver of the system, and that works fairly well. And that needs to be enhanced. In other words, somebody has to build that at a more detailed solid-state level. I use more of a macroscopic demonstration of it, but it can be done at a solid-state level. So those that have solid-state interest, that is an area that I would go after. The other thing is you can enhance the electric field measurements. I talked about that. You can get extended range by changing your FET and extended sensitivity in that same process. I showed you two-dimensional images. There's no reason why you can't generate a 3D image of any object by rotating the systems around yet another axis. The other area in 3D imaging we already have and have done is that you can actually take that 2D image of which you have the electric field vector already, and you can back project into the system and look at different depths. So we already have that capability now, and that capability would have to be expanded to go forward, and that would be very similar to reconstruction, to X-ray tomography reconstruction. So that whole area could be worked on to be expanded for characterizing within objects. Other commercialization opportunities are, now that we've seen the work with the fire activity, there's some fire looking at burning and things like that, as well as product safety. You can look at the whole combustion process in a different way. Also, remote characterization of ion generation and flow. That's useful for space engine control, satellites, etc. I talked about the ESD applications. Semiconductor manufacturing, designer materials, where you're embedding particles and things like that, such as additive manufacturing, where you have possibly charged particles moving around, controlling those charged particles, for example, and knowing what fields you're using to control those particles as they're being placed. The other element is that I showed you electric field imaging through all these, through the first part here, the first section. There's no reason why you can't add another technology onto electric field imaging. In other words, you can actually use phonons and with electric field imaging to generate electric dipoles within a material. For instance, you could have something vibrating, I'll use sound as an example. You could have sound vibrate an object inside a system if the two objects have different triboelectric properties. Every time they separate, they create a dipole electric field, and you can see that field outside externally, remotely, and we have already done that. It's on the phonon EFI. I didn't show that as a demonstration here, but we do that with sort of like a cell phone mode of vibrations if you want to get the kind of frequencies we're talking about. That same field has extension you can generate antennas now using vibrating dissimilar materials, and so that's another area that comes forward from this from the electric field imaging. So you can add multiple technologies to it. In this case, I've added phonon to do that. And I think I would stop there. The other one I wanted to add is in medical properties, is that if you're looking at the electric properties of blood, for example, in dried blood, there's some work in that area under tension to look at that properties related to cancer and things like that. I'm not familiar with the area at all, other than I was made aware that that was an area of interest, and so I just point out that electric field imaging and organic systems is also an area that would need to be worked, could maybe worked. And I think with that, I'm going to stop right there and ready for questions.
All right. Well, thank you, Ed. What an interesting technology and a lot of commercialization opportunities there. So one of the primary goals for our technology transfer office here at NASA Langley is to license these NASA inventions like the electric field imaging system to industry for the greater benefit of the public. So before we get to the Q&A session, and we've got a lot of great questions coming in, my colleague Jennifer Viudez is going to give a brief overview on how technology licensing works at NASA Langley. Jennifer?
Thank you, Sean, and thank you, Dr. Generazio. I always enjoy listening to Dr. Generazio. He has such interesting things to say, and he did provide so many interesting commercialization opportunities to develop, to have industry to develop. So I want to say hello. I am Jennifer Viudez, and good afternoon to everyone. I'm going to give just a brief overview of our technology licensing process at Langley, changing gears here. This chart is a logo chart. I just want to give you an idea of some of the universities and different companies that we already have partnerships with and that we have already licensed to, and just get the point across that we have a wide range of partners, and we do license to small businesses, large businesses, and everything in between. So you just heard about Ed's electric field imaging system, but Langley also has a full portfolio of intellectual property, which you can search on our website, the Technology Gateway, that you see listed here, technologygateway.nasa.gov. Each of the NASA centers has its own expertise, but because of our contributions at this center, NASA Langley, to aeronautics, science, space technology, and human exploration, our intellectual property tends to fall into the following categories that you see here: advanced materials, aerospace applications, sensors and detectors, and software and simulation, and much, much more. So I encourage you to visit our website and to use keywords to search possible technologies that you may be interested in. We have a very robust search engine that you will probably find very helpful. Many people are familiar with licenses. A standard commercial license allows the non-NASA entity access to the technology, to test the technology, and to implement it into a system, a service, or a product that may and hopefully result in sales. Licenses can be negotiated to be exclusive, partially exclusive, or non-exclusive. And what that means is that it defines the level of treatment your particular field of use receives. So for example, if NASA has an energy harvester technology, which we do, and you're in the business of selling Fitbits, you may want exclusivity in the field of watches. That's just an example. And all of this, the field of use and other types of business applications, are all negotiated. We have other types of licenses other than the standard commercial license, and that includes the startup license and evaluation license. Our startup license is relatively new and would be very attractive to startup businesses because it allows you to keep money in your pocket. It allows you to keep resources for a longer period of time because there is no upfront fee at the signing of the license, and there are no royalties due for the first 3 years. So it gives you a chance to get your business up and running off the ground. Another possibility is the evaluation license. This license is normally put in place for 1 to 2 years. It's very similar to the commercial license where you receive access to the technology, you can test it, see if it works for your application and for what you want to do, and it's a flat $2,500 fee. You can do anything with the evaluation license other than sell a product. We talked about how to search Langley's technologies on the Technology Gateway website. It is also on this website where you can find all the information you need to get a license started. For any type of license, you will submit an application. That's the first step. The amount of information you provide depends on the license you are seeking. And here you will see some examples of the info that you will need to provide on the application. And again, it is listed, there is a link on the technologygateway.nasa.gov website, and you can see the full applications there. So this is basically what I've talked about so far this afternoon. It is our licensing process and review. First, you will find a technology that fits your business need. Next, you will contact our office and we will talk about it. This may include conversations with the inventor to give you a chance to ask questions and to get clarification on the technology you propose to license. You submit an application and wait for our office to review it. Once it is acceptable, and if it is acceptable, we'll notify you, and we'll begin to negotiate a draft license. Once we agree on all of the terms, we will sign, both parties will sign, and we will have an executed license. All of this activity you see listed here could take anywhere between days and months, depending on the negotiation process. That is all the information I have for you today, and if there are any questions for me, then feel free to submit them into the chat box, and we'll answer them during the Q&A session, or we will follow up by email after the webinar, and the questions and answers, same thing goes for Dr. Generazio's presentation. And thank you for your time today.
Great, thank you, Jennifer. So we have set aside some additional time to answer some of the questions from the audience, and we've gotten a lot of them so far. So thank you very much. If you can continue to submit your questions in the chat box. We may not get to all of them during this Q&A session, but we will absolutely, as Jennifer just said, follow up with you after the webinar and make sure that your question is answered. So let me just see and start to look through. So Ed, the first question is for you. Excuse me. It is the electric potential and electric field imaging solution the same for all the applications that you described?
No. Since electric field imaging is new, I'm learning this area answer to this in real time here. And no, it's different for, there are classes. If you want to do inspections of containers, for instance, that have no charged items in them, charged components inside, you may want to use a quasi-static generator and an electric field sensor on the other side, an EAT sensor on the other side, whether it be a linear array or a two-dimensional array. However, if you have, so that's one example. However, if you have a circuit that is charged and discharging, you may not need to use a quasi-static generator. It doesn't add more value. You can just use the two-dimensional array or the linear array or even a point system. Those are just some examples, but everyone is pretty much different. Building a security system for a room may use an ephemeral sensor, may use just one sensor operating in an ephemeral mode. So it depends on the specific requirement, what you're looking for. Depends on what kind of system you're going to use.
Great. Okay. So the next question is there a way to select or vary the intensity, field of view, and other parameters to meet specific application needs?
Yes. Right now, the field of view, once you say field of view, you're pretty much indicating that there's some sort of vectors involved. And once you have the electric field vector, for instance, a two-dimensional array, or using the linear array with a conveyor scanning of the system, once you have that information, you have in the plane that you took the measurements, you have a set of electric field vectors at every point in that plane. And you can take those vectors and you can back project into the system. Basically, you're doing exactly what a microscope does, is you're actually focusing into the system, looking at different areas through the system. Now, it's a little different in electric field imaging versus optics. In electric field imaging, the electric field will be distorted by the dielectric properties of each of the constituent components that you're looking at as you go deeper into the system. So you can adjust your field of view by setting the different distances that you're looking at. So it's very similar to optics.
All right, great. So the next question is, how does EFI differ from other technologies that image electric and magnetic fields?
One of the first things is that electric field imaging images charge, where the electric field, but it's really indicating where the charge source is. Other technologies such as electromagnetic, for instance, X-rays electromagnetic, as well as microwave, they're not imaging the charges, they're imaging, X-rays are imaging density, for example, and it's not imaging the charge. So the difference is electric field imaging is imaging the charges, presence of charge, where these other systems are not. And the other key component is that when measuring electric field imaging, it's quantitative with respect to the charge that you're measuring. It's a quantitative measurement, and some other systems that have attempted to measure, do electric field imaging, they're giving you a signature or an indication that something exists there, but it's not quantitative, so you really can't reconstruct the actual object or within the object itself. And so that's the difference. The electric field imaging is looking at charges, the electric field from charges, presence of charges, charge distribution, and primarily the biggest part is quantitative. And so you can reconstruct the objects that the charges are on, basically.
All right, Ed, we're actually going to turn to Jennifer for a second because we've got a question about licensing. For me, the question is, Jennifer, for me to license and integrate this technology into my product, I may need technical support. Can I contract NASA to assist with my specific application?
Yes, and we often will partner with licensees. We don't like to just send folks out into the wild to try to figure out every single thing by themselves. We certainly do support a short amount of hours with our inventors to have phone conversations, to potentially visit our center, to visit the labs. Once we get past a certain point of time and it's discovered that more lab testing may be needed, more time with the inventor, if the time is available, may be needed, then we enter into what's called a Space Act Agreement. A Space Act Agreement is simply the document that allows NASA to legally partner with other organizations. So the short answer is yes, you do receive some support from the inventors as time allows.
Great, thank you. All right, Ed, back to you. Does EFI need to have an active source, a transmitter, as it were, or can it detect passive electric fields?
No, you don't need it can detect passive electric fields. For instance, the gun in the container, that image can be done without the quasi-static generator. So no, you don't need a source. If the item itself is not charged, then you would need some sort of, you either use a method like the phone-on EFI where you actually have to create some other source internal to the object, or you have to apply an external field. But no, you don't. It can run both ways. If there's charges inside the system that are already there, if there's an electric field emanating from an object, then you can use an individual sensor without a source.
Okay, so we're just going to do a few more questions. And again, if we don't get to yours today, we will definitely get to it after the webinar by email. But the next question is the technology easily transportable?
Yes. The first two-dimensional array was handheld. It was also low cost. By the way, all these systems are very low cost in their prototype configurations. The first one was low cost. It ran off a 9-volt battery, typical 9-volt battery, and it was very light, probably less than a quarter pound, and transportable, held in the hand.
Okay, and so the next question is actually about the durability. The viewer asked, how durable is the system? Can it be made to withstand harsh environments?
That's a good question. The durability. Well, I guess I have to let me imagine what the harsh environments are. There are harsh environments in marine areas, in space, atmospheric, subterranean. Let's go through those. The electric field imaging system itself will survive all of those areas. It may have to be containerized. For instance, if it's raining out, a storm may have to be containerized, but it will still measure the electric potential, electric field in those environments. And the interesting activity in there is the method for containerization, and the electric field imaging system itself will help define the best containerization method for it. But yes, it can be made extremely durable. Extremely durable, and it depends on if you happen to put it into, let's say you put it, it's going to get struck by lightning, and then it's not going to be durable. That's going to be a tough one to get around. But all the others, I don't see any problems with.
Great. Okay, so this will be the last question of the webinar. The question is, can we do in real time imaging on a single plane?
Okay, on a single plane. Yes, I haven't done that. I showed real-time images of potential in a 2D array. That was the ion gun and in the flame. And from that, that was only on a plane, and it was just the electric potential. If the 2D array is modified slightly, and it will be able to get the electric potential at two different distances from the flame simultaneously, and that's just a matter of design. And once you do that, you can get the electric field in a plane. I want to point out that electric fields very rarely exist in a single plane unless it was entirely designed to be in a single plane. Almost all that I've seen, all the ones that I'm testing here, they're showing to go in 3 dimensions. And so when you try and get the electric field in a singular plane, you're actually just collecting the elements along that plane, and that's helpful in some cases. But yes, it's doable with these systems. You can use 2 electric field sensors at 2 different distances also to get in the plane. So yes.
Great. Well, that is all the time we have for questions today. I want to thank you, Ed and Jennifer, for your presentations today, and especially thank the audience out there for coming and listening to hear about the electric field imaging system. Again, if we did not get to your question during the Q&A session, we will follow up with you by email within the next week. If you have any additional questions, please feel free to submit them to that email address that says larkdltechnologygateway@mail.nasa.gov. You can also reach us through our website, the Technology Gateway, which is technologygateway.nasa.gov. And once again, we really appreciate you taking the time to hear about the NASA's electric field imaging system today. I hope you all have a wonderful afternoon.